So I'd like to welcome everyone to today's 7th edition of the NAI webinar series. Some of you I see have been coming back, so really nice to see you again. And today we have Gustav Šír presenting his webinar on neurosymbolic learning in relational domains, graph, neural networks, and beyond. Just a little bit of housekeeping in case you read the messages or not. Today's webinar is being recorded and we will post it afterwards on the NeuroSymbolic AI YouTube channel. There's a link in the chat if you've not been there. And please stay muted, everyone that's watching. And after the presentation ends, we will start the Q&A session. So if you have a question for Gustav, you can unmute yourself and ask your questions. Or if you don't want to say it out loud, you can put it in the chat and we will be monitoring there as well. And then today's presenter is Gustav Šír, an assistant professor in the Intelligent Data Analysis Lab at the Czech Technical University in Prague. His research in artificial intelligence has focused on deep relational machine learning, which also resulted in his dissertation thesis, a book from iOS Press, and it's called Deep Learning with Relational Logic Representations. There's also a link in the chat to the book if you're interested. Gustav is also a member of the editorial board of the NeuroSymbolic AI Journal, which is the journal of this webinar series. And today he's presenting a webinar on neurosymbolic learning in relational domains, graph, neural networks, and beyond. So take it away, Gustav, and everyone please throw it on mute if you've not already. Thanks.
Thank you, Lauren, for the introduction. So let me try sharing my screen. So thanks everyone for joining this webinar. I'll be speaking pretty broadly about this series of recent works that I've been working on with my colleagues and students. And the work revolves quite a lot around graph neural networks that are recently becoming increasingly more popular in AI broadly and including the neurosymbolic learning community, I would say. So I will build from that and move then to some actual neurosymbolic learning with this neurologic framework that I've been developing with my colleagues for more than 10 years now to show what more can be done in relational domains beyond the graph neural nets. All right. So this is the structure of the talk. Is after some general introduction, I will overview what can be done with the graph neural nets in the relational domains that can, to some extent, be considered as symbolic. So this involves combinatorial optimization, planning, and learning from relational databases. And then I'll move to some actual neurosymbolic learning with the neurologic framework, explain it on a series of commonly intuitively known neural architectures, all the way to the graph neural nets again. And then finally, we will look at how that can be used to address the relational learning domains again, while doing something a bit more than the GNNs. Now, in this talk, I will consider the problem of neural symbolic integration heavily from a learning representation perspective, combining the benefits of, on one hand, the discrete representations of symbolic AI, which are commonly data efficient, interpretable, and allow for systematic generalization. And these are being applied in various symbolic AI tasks, such as reasoning or planning. And then on the other hand, we have the continuous representations from statistical or neural approaches, which are commonly computationally efficient, and they are robust to noise and uncertainty. And these are commonly used in all of machine learning these days. Now, let us take a little bit closer look of what we are actually trying to integrate. So, on one hand, the concept of deep learning probably needs no introduction, but it is this machine learning paradigm where we use gradient descent to train parameters of nested functions, which can be conveniently viewed through their computational graphs, commonly referred to as neural networks. And now the main idea here is in learning of latent representations, which are commonly viewed as the hidden layers in these networks. And now the main limitation of classic deep learning I will address throughout this talk is the form of these representations, which, similarly to the input data themselves, is commonly constrained to fixed-size numeric tensors. And now on the other side of the machine learning spectrum, there is this rather unorthodox community of symbolic learning, also called relational learning or inductive logic programming, which uses the language of first order or relational logic to capture richly structured learning representations in the form of various annotated graphs, or hypergraphs, ontologies, and so on, as well as complex relational learning patterns extracted from these. And now the inference with these models can also be conveniently visualized in the form of computational graphs, commonly referred to as proof trees or resolution trees. And now the research question we try to tackle is how to combine these two paradigms to make neural networks learn with these rich symbolic relational learning representations, or from the other perspective, how to use gradient descent for the relational or symbolic learning. And in a sense, a very similar integration has been explored for decades already in the field called statistical relational learning, exploring this kind of paradox we have in machine learning between the so-called statistical, or sometimes referred to as propositional, and relational representations. Now, the thing is that the input observations in machine learning have traditionally been limited to the form of numeric vectors, also commonly called feature vectors. And this is what has traditionally been expected by virtually any machine learning library, and consequently basically turning the classical machine learning into classic multivariate statistics, estimating joint probability distributions upon these feature vector spaces. However, if you just look around to see how the actual real-world data looks like, it is mostly not stored in such numeric vectors or tensors, but in the interlinked structures of the internet pages, or social networks, engineering databases, and so on. And so these are inherently relational data that are naturally stored in their structured form of various graphs or knowledge graphs and hypergraphs, such as relational databases. And so perhaps the first thing that comes to mind is if we can't just turn these structures into the feature vectors, and then everything goes back to normal, so we can use our standard machine learning pipelines. And this has for long been the primary way to do machine learning with these structures, often referred to as propositionalization. So for instance, one could calculate various statistics upon these structures, such as counting out nodes or edges or subgraphs, etc. However, there's a problem with turning relational structures into such vectors, since there's obviously no way of mapping unbound relational structures into any fixed size representation without some unwanted loss of information. Nevertheless, by now we already know that this is not necessary to do, as we can also learn directly from graph structured data representations with models such as graph neural networks that have recently become extremely popular, exactly because they allow to skip that pre-processing step in that classic deep learning, end-to-end learning fashion. But of course, this also requires to turn the input data into graphs if necessary. This is sometimes referred to as graphicalization. Now, obviously, dealing with differently sized input feature spaces would be a problem for classic machine learning. But even if we restrict ourselves to fixed size structures, designing a suitable, unambiguous representation in the form of a numeric vector or tensor is still problematic, which I was trying to demonstrate with this simple graph, ABCD, in here, a circle, which corresponds to all these different adjacency matrices. They all represent the same graph. And so this boils down to the core idea with the graph neural nets, which is that they are invariant to this ambiguity stemming from the ad hoc node ordering in this tensor or matrix representation, which they do by structuring the computational graphs such that they dynamically reflect the structure of the input graphs themselves. Right? And this is kind of a core distinguishing idea or property of all truly relational models, and we will see a lot of that later on throughout the presentation. And now this dynamic neural computation makes the GNNs already quite suitable to address a number of relational domains and problems that are kind of symbolic in nature. So particularly we'll look at the combinatorial optimization, planning, and relational databases. So starting with the combinatorial optimization, which underlies many, perhaps if not all, of the classic symbolic AI problems. So that's naturally an interesting area for application of graph neural nets. Generally, there are various deep learning approaches to combinatorial optimization, but one idea that has gained kind of particular attention recently due to its generality and kind of interpretable physical intuition are the so-called physics-inspired graph neural networks based on the popular Ising spin chains. You might have heard about those, especially in context of quantum computing. Now, the idea is actually very simple. These physics-inspired GNNs leverage a specific quadratic loss to encode the objective of some unconstrained binary optimization problem, which then enables for simple unsupervised training to converge on solutions that minimize the subjective or Hamiltonian of the system. Such as in this simple example with the graph cut combinatorial problem, we encode the problem's decision variables as nodes in the graph, and then their pairwise interactions then correspond to the edges that are associated with certain penalties. And on the diagonal, we then have values associated with the solution itself. And this is completely analogous to the classic Ising model. And then we just run stochastic gradient descent to minimize this objective, the respective Hamiltonian of the system, hopefully settling down in some global minimum corresponding to the solution. And so that kind of works. And this framework has been demonstrated to yield some promising results in various combinatorial problems. There have been even papers in Nature on that. But we have studied that a little bit more and shown that the performance of these physics-inspired GNNs kind of systematically plummets with an increasing density of the combinatorial problem graphs. So in this recent paper, we revealed that this is kind of stemming from the discrepancy between the relaxed real-valued, naturally real-valued GNN outputs and the naturally binary valued problem solutions to the combinatorial task, which is kind of a discrepancy pretty familiar to those working around the NeuroSymbolic integration. And so to address that discrepancy, we proposed a somewhat more principled alternative to the naive rounding strategy that is being currently used in the physics-inspired GNNs by building on insights from binarized neural networks and fuzzy logic operations, which is kind of classic NeuroSymbolic tricks. And that enabled us to demonstrate some significant performance improvements of the physics-inspired GNNs, and especially in the denser combinatorial optimization settings. And another, perhaps even more classical setting is where the GNNs are being used as a heuristic estimator within some classic search procedures, such as A-star, such as what we did here with the Rubik's Cube problem. Now, the Rubik's Cube is a fixed-size problem structure, which allows for a naive application of neural networks, which is exactly what people did before. And again, it's another Nature paper. Now, the thing is that similarly to the graph permutation ambiguity with the adjacency matrices mentioned before, there are various intriguing symmetry groups inherent to this combinatorial domain of Rubik's Cube. It's just that they are slightly more involved than the simple permutation or rotation invariance explored normally with neural nets through this so-called geometric deep learning, which is kind of this umbrella term for deep learning models, such as the graph neural nets, those that exhibit some sort of symmetry invariance. So what we did here is another extension of the GNNs that kind of explicitly leverages these symmetries from the Rubik's Cube group, and again shown some improvements with that. Now, this employment of GNNs as a heuristic in a search procedure is then very close to another symbolic AI field, which is classical planning, which the GNNs are now penetrating quite actively into. Now, the application of GNNs in planning boils down quite directly to the aforementioned graphicalization problem. Now, this is because in heuristic planning, the input state to the scoring model is not a graph, but it's a relational structure. Such as shown here in this simple example. We have three objects, T, L1, L2, and these form a set of atoms. So we have some nullary atoms, unary atoms, binary atoms, and one ternary atom defined upon those. And now there are basically three sensible options of turning that relational structure into a graph. Either we connect objects to objects, or we connect atoms to atoms, or we connect objects to atoms. Which is kind of what these three diagrams are roughly showing. Now, the aforementioned GNN's invariance under the permutation symmetry significantly improves their learning generalization because they see all those different adjacency matrices as the same one. However, this comes at the cost of limited expressive power, which is in contrast to the commonly known universal expressiveness of standard feed-forward neural networks. Particularly, GNNs cannot distinguish between graphs beyond the constraints imposed by the one-dimensional Weisfer-Lehmann test, a popular graph isomorphism refutation check. Or likewise, from another perspective, GNNs can distinguish between graphs that satisfy identical C2 sentences. And this is in C2 logic, where C2 is basically this fragment of first-order logic with counting quantifiers and at most 2 variables. So for instance, with C2, you can form sentences like, if there is a blue node that has at most 2 green neighbors, and so on and so on. And so, for instance, these 2 graphs are indistinguishable for a classic GNN, which, as you can probably imagine, is a problem if we have 2 such planning states that we are not able to distinguish from another. So consequently, the expressiveness of the graph encoding, coupled with a specific GNN architecture, depends quite crucially on the absence of such indistinguishable state pairs that would require distinct actions in an optimal planning policy. So we need to distinguish those. And this is kind of what we investigated in this paper, providing some theoretical and statistical exploration of such situations in classic PDDL domains across those various graph encodings, objects to objects, objects to atoms, and so on, and across various classic planning domains. And yeah, the result was not very surprising. There's no free lunch when it comes to expressiveness also. The larger the encodings, the more expressive they are, while some domains are inherently more difficult than others. But also not all GNNs behave the same in practice. And then we just kind of followed up on that with a comparative study evaluating their practical effectiveness instead of the expressiveness in an actual planning competition in the IPC. And there, so that's another paper actually to be presented pretty soon at AAAI. And here our results indicated basically that actually the smallest encoding, the one encoding connecting objects to objects, outperforms the rest due to its fast evaluation times when employed within a search procedure and the overall informativeness of the heuristic. So this is just comparing the numbers of expanded states during the search. So the lower, the better. And moreover, the overall coverage measured on the IPC benchmarks almost reached that of some of the state-of-the-art planners, such as Llama. Although, like, frankly, I think should be said that GNNs are not really yet there in planning. They're not the state-of-the-art. That's yet to come, probably. So that was planning, and with that, we zoom in again on the learning representations and the graphicalization problem by considering directly the primary format of relational learning, which I would say is the relational databases. So much of the real-world data is actually stored in relational databases, as you probably know, which is exactly what a planning state looks like, actually. It's a small relational database. Now, the thing with this data format of relational databases is that it differs significantly from the classic tabular data format, those feature vectors normally used in machine learning, in that we may have several tables or relations that are interconnected with foreign keys. So this means that rows in these tables composed of the respective column attributes can no longer be considered as IID feature vectors, that classic assumption in all statistical learning, but instead we need to take into account the structure of the whole database instead. And yeah, so this is kind of what we did in this other paper. Particularly, we considered the structure of a database as a 2-level multi-relational hypergraph, where the relations from the database tables form hyperedges over the respective individual column attributes. And then these are further interconnected by another set of hyperedges corresponding to the foreign key constraints between the different relations. Now, the main contribution of the paper was an introduction of a custom modular message passing scheme on that multi-relational hypergraph representation, effectively allowing for end-to-end deep relational learning directly from databases. And now the scheme, again, is dynamically reflected in the computational graph of this kind of complex neural architecture, the details of which are not so important in here. Let's say it's kind of a combination of the graph neural nets again with the transformer architecture. And yeah, similar here, this is just a depiction of the overall workflow of the deep relational learning where that message passing scheme is embedded. Basically, it just highlights that we indeed can learn end-to-end from kind of basically directly database connection strings. That means that there is no propositionalization or other pre-processing involved, although there is obviously still kind of the graphicalization happening in a sense, as we are then able to use the graph neural nets on top of that. And so we compared several instantiation of that deep relational learning scheme against some representative models from various machine learning fields, including tabular models, statistical relational learning, propositionalization, and NeuroSymbolic integration, showing some pretty promising results over a wide range of database datasets. I can find the framework online, including all the results. Yeah, also in the paper. Yeah, so please check it out if interested in deep learning from relational databases. Okay, and so with that, we leave the space of the graphicalization and combining existing neural architectures for something actually neurosymbolic by design, kind of starting from scratch. So something that learns directly with the relational representations, which is this neurologic framework. All right, so firstly, let's start again on the classic propositional level of neurosymbolic integration. So perhaps surprisingly to some, the propositional correspondence between the neural and logical computing has been quite well established throughout history, dating all the way back to the first perceptron by McCulloch and Pitts, which was actually thought to emulate logic gates. That's how the paper was called. And the idea was based now on the now commonly demonstrated fact that logical connectives of conjunction and disjunction can be easily encoded by binary threshold units with weights, so that means the perceptrons. And a number of actual systems reflecting this neurosymbolic correspondence kind of emerged throughout the 90s already, such as the popular K-BAN, knowledge-based artificial neural networks model. And the thing is that while this correspondence between the propositional logic formula and neural networks has been kind of direct, transferring the same principle to the relational setting has been quite a challenge. And now the issue is that in the propositional setting, only the binary values of the existing input propositions, such as the sunny, hot, dark, and so on in here, change, while the structure of the logical program is being fixed, and that does not change. So this is kind of easy to think of as a Boolean circuit, the neural network, working on top of the propositional interpretation, which is just some one hot encoded feature vector or multi-hot encoded vector. However, the relational program input interpretations can no longer be thought as such independent values over a fixed number of propositions, but it's an unbound set of related facts that are true in some given world, such as the planning state or a relational database. And now, obviously, this issue, as I put it out, is intimately related to the aforementioned problem of relational learning representations. And it is thus not surprising that to capture the relational logic expressiveness with neural networks, a lot of neurosymbolic research turned to similar techniques that machine learning practitioners use to deal with as relational data representations, such as the propositionalization or tensorization. And this is also kind of how I got into neurosymbolic learning by starting from the background in statistical relational learning. And particularly in our approach, we were kind of inspired by the so-called lifted graphical models from the SRL, which use this language of relational logic clauses extended with some learnable weights to serve as templates for defining standard, also called ground graphical models, such as in this popular example of a Markov logic network about smokers being unfolded into a standard Markov network. And the only interesting thing to note here in the ground network are the shared weights and generally the symmetries that are induced by the repeated use of the rules or the formulas from the template. So with that kind of motivation, we can move to introducing the framework, the lifted relational neural networks, or the neurologic for short, which uses this lifting idea to address relational learning in neural networks instead of graphical models. So syntactically, somewhat similarly to the Markov logic nets, an LRNN is a set of weighted definite clauses. So now these are commonly written in the form of implication rules in the context of logic programming, which we follow pretty closely. And similarly, the learning examples themselves are also expressed in weighted logic, most commonly as sets of weighted facts. And then instead of inputting an example into a model, as we know from the classic machine learning, we just merge these two representations and interpret the result as a neural network. And the semantics of that process is as follows. We compute the least hairbrine model of the logical sample to obtain all valid groundings of all the rules in the template. And then we map this ground logical model into a neural model composed of these 4 types of computational nodes that I will try to demonstrate shortly. And then these neural nets then can just be used to optimize the weights originally associated with those rules by just regular means of gradient descent. Now, instead of going deeper into the framework, which you can find the paper and online, I will just demonstrate it on a series of simple, intuitive, hopefully commonly known examples of neural architectures. So let us revisit again the simplest possible concept, which is the standard feed-forward neural net modeling in the style of the K-band model. So this is basically just about assigning names to the individual neurons in the network corresponding to the logical propositions from the template, such as the dark, cold, sunny, and hot here. You then correspond to the fact nodes in the network. And then there are rule nodes capturing the respective conjunctions between these facts, commonly under some smooth fuzzy logic interpretation for them to be differentiable. And then these form input into so-called atom nodes, representing, again, logical propositions from the template, such as the forecast proposition here, associated with logical disjunction, again, under some fuzzy logic interpretation for combining the different rules together. And then finally, the weights from the rules are just directly mapped to the corresponding places in the network, similarly to the Markov logic nets. Now, with the relational templating that can contain logical variables, things get much more interesting as we can get to more advanced neural architectures. So, for instance, here is an encoding of a standard convolutional net, simplified to a single dimension for visual clarity, the core of which can be encoded by this single rule on top, which expresses the relational pattern that each 3 objects, A, B, and C, that are consecutive in some sense, where A is next to B, B is next to C, should be jointly parametrized, so these are the parameters, and aggregated in some latent representation, let's call it H. And now this rule, when grounded over some sequential structure, such as 1, 2, 3, 4, 5 here, then directly corresponds to the computation induced by application of a convolutional filter in CNNs, where we will have the input pixel values corresponding to the weighted fact nodes, rule nodes will correspond to the individual applications of the convolutional filter, and finally we have aggregation nodes, new ones, capturing basically the pooling operation. Now, that example of a CNN might seem a bit cumbersome as there are inherent assumptions about the structure of the pixel grids that are implicit in the CNN architecture, while with this more general relational framework, we have to make them explicit. But it kind of highlights another important aspect of relational models, which is weight sharing in their computational graphs, reflecting the necessity to capture the respective domain symmetries again. And that applies whether we talk the permutation symmetries in the MLNs or translation symmetries in the CNNs. And now this generic principle of relational NeuroSymbolic encoding then comes up kind of more naturally for various recurrent and recursive neural models, which can be represented very elegantly since there are fewer assumptions here. And recursion is obviously a very natural concept in logic programming. So recursive unfolding of the weighted templates over a recursive data structure, such as various sequences or trees corresponding to the recurrent and recursive networks, respectively, is pretty concise and elegant in the framework. And now this correspondence then becomes even more natural for the graph neural networks. So let us revisit them again. So in the logical terms, the idea behind GNNs is simply that the hidden representation H of some node V in some layer I is determined by some parameterized transformation of some other nodes U, such that there is an edge between V and U. And further, in some GNN models, we might also want to combine this with the representation of the same node V from the previous layer. And now this logical template, basically directly encoding the so-called message passing rule in GNNs, will automatically induce the exact same computation graph you would normally get with the classic GNNs when written procedurally in classic deep learning frameworks such as PyTorch or TensorFlow. And now just please note that these rules are not some abstract mathematical notation as commonly used for representing GNNs in the paper, but they're the actual code that can be directly run in the framework. So that was how simply you can capture GNN principles in the logical framework, but that is by no means limited or even optimized for this model class. So this means that I can directly go further to learn with various heterogeneous multi-relational graphs, hypergraphs, design various subgraph, metagraph GNNs, completely new message passing schemes, and so on and so on. If you're interested in that, you can check out this paper. And of course, you can find the framework online. And so with that kind of promo, let me move to show some of the actual interesting examples of what can additionally be done beyond the GNNs. So the first example I have here is just how we can go beyond the classic Weisfall-Lehmann expressiveness limit that improves the basic GNN performance in molecular data sets. And that is generalizing the message passing scheme to operate on the level of atom rings instead of just nodes and edges as done in the classic GNNs. And again, this is pretty easy to do with the rules. You encode the ring as a conjunctive pattern composed of the individual edges. You add some learnable parameters, some learnable transformation on top of that, while aggregating the representation of the individual contained atoms back into the ring representation, which you can then propagate back into the individual atoms in the subsequent layer. And we did find this to provide some improvement by learning with molecular, especially organic data sets quite some time ago. And these days, this is quite a standard trick with the GNNs. So with that, we can revisit the more, say, principled problem of deep learning with the relational databases. Now, building directly on the relational logic templating, this is completely natural in the neurologic framework, as there is no need to do any graphicalization or preprocessing like that. So this is basically how the underlying mapping looks like in the actual templating language, which is kind of embedded in Python. So that's why we put this R, like relation dot, and then the name of the relation, use the strings for the constants and so on. Moreover, this also offers an interesting alternative view back on the basic vanilla GNNs again, which which is again like this simple rule in here encoded in the Python syntax, and which instead of being interpreted as the message passing rule, again, can be seen as performing simple SQL operations. So particularly this classic message passing rule, message2 or some hidden representation of X is implied by its neighbors, can be interpreted in SQL as follows. So it basically says join tables or the relations message1 and edge on their commonly shared column Y, then group by X, which is what's in the head of the rule, and aggregate the resulting values into a new table or view that you call message2. So that's what the GNNs are actually doing, and that's exactly how it works in the framework, which then allows you to, for instance, evaluate trained GNN models directly in database engines as these parameterized SQL operations. Now, revisiting planning. There are also some very interesting avenues for neurosymbolic learning, as basically the PDDL language in planning is, again, very close to the symbolic language of relational rules and logic programming. So one can not only learn directly from the relational states, but also incorporate other domain knowledge, such as the planning actions to learn better planning policies. And this is kind of what we did in another recent paper, where we took such a symbolic background knowledge to create some initial satisficing suboptimal policy, such as the one commonly known for the blocks word problem, roughly shown in here, where the details are not important, but basically it says unstuck all wrongly placed blocks and then place them back on top of those that are already well placed, where well placed is this recursively defined predicate. And then using the neurologic framework, such a symbolic policy can then be differentiated through and learned on top to further tune it for higher quality or optimality. And yeah, this is again just a visual depiction of the idea. We have some planning states. Those are represented as sets of relational atoms again. And then we have some background knowledge encoding some low quality policy, initial policy. And then that is translated into some dynamically structured neural policy models that learn to directly predict the best out of the valid actions. All right. And yeah, with that, I'll move to the final part, which is a concluding kind of a computational perspective on the whole discussed concept of deep relational learning. So let us revisit again the symmetries in relational models, which are not only interesting from the invariance and therefore generalization point of view, but also computationally. And the point is that if you apply simple computation rules, such as the GNN message passing rule we've seen before, to input structures that exhibit some sort of symmetries, then the induced computational graphs will contain these symmetries too. So that is kind of shown in the picture here. The molecule of methane has this central reflection point through the carbon atom. And so the computational graph, which is this one, will kind of necessarily share this central symmetry through the carbon atom node, and as well as all of its latent representations too. All right. So this means that if we can detect these repetitions, basically, we can effectively compress all these equivalent subcomputations, which can then be carried out only once and broadcast them back into the respective places in that dynamic computation graph. Right. So that's another paper. Yeah, and the point is that classic relational learning tricks like that one can then, interestingly, be used to speed up even classic GNNs, which might be surprising to some. So yeah, this is kind of what we did here while comparing against some of the most popular and fastest GNN frameworks, such as PyTorch Geometric, over standard GNN models and classic benchmarks, for instance, for learning with molecules. And yeah, so that was for a non-batched setting, so going vanilla SGD one by one, which is kind of simpler version that was there in the framework originally, as well as some more recent full batched setting with full GPU acceleration. That, to be honest, contains a lot of other tricks than just the symmetry, to be fair. But the main point of that is that the deep relational models, including simple GNNs, do not benefit from the classic GPU acceleration in the same way as the standard static neural networks do, which has to do with the discussed, dynamic, sparse, irregular nature of their underlying computation graphs, which is kind of problematic for the common matrix multiplication-based hardware and software stacks that we currently have. And yeah, this highlights the one finally important point I was trying to make here in this recent NeuroSymbolic AI journal paper, which is that there is currently kind of a significant hardware and software library in play that benefits the kind of monopoly of the currently prominent dense tensor-based deep learning with static computation graphs, which is, however, largely insufficient for symbolic computation that contains a lot of branching and looping, recursion, and so on, and therefore also kind of suboptimal for fully expressive neural symbolic integration, particularly in the discussed relational setting. All right, so that kind of concludes my presentation. I know it was kind of quick, shallow overview of a broad range of topics, but you can find more information in the papers. There's also a series of Medium articles that should be like more approachable to general public. Of course, you can also find the frameworks on GitHub, all of them, and that you can then use in exploring your own ideas for similar relational neurosymbolic learning in such domains. So with that, I thank you for your attention. And last but not least, I thank to all my wonderful colleagues and students have been co-authoring the papers with me and working on the framework, particularly Lukáš Zahradník, Jakub Peleška, Martin Krucký, Honza Neumann, Dilon Chen, Rostya Horčík, Vondra Kuželka, and Filip Železný. All right, that's it for me. Thank you again. I'm looking forward to your questions.
Thank you, Gustav. That was really great. And we already have one question I see in the comments from while you were presenting, if a copy of the slides can be shared.
Sure, I hope so. Yeah, you can post them wherever you like.
Yeah, all right. Well, then to the one asking the question, yes, we will provide the slides. We will also send a link to the webinar afterwards. So in that email, if you've registered, if you're here, you probably registered, then you will be able to get a copy. Yeah. So if anyone has questions, we'll move into the Q&A, and feel free to either raise your hand or unmute yourself or put your question in the chat. Don't be scared.
Yeah, of course, you can also reach me out on the NeuroSymbolic Slack later if interested, or just via email. I know the presentation was a little bit rushed and broad overview, but no question is too silly.
Yeah. Also, like he said, the NeuroSymbolic Slack. If you are not in the NeuroSymbolic Slack, just maybe place your email and we can add you to the Slack, or you can, when I send the webinar, reply and ask to be added to the Slack. Yeah. Any takers? If not, then I think we can wrap it up and let the conversation continue in the NeuroSymbolic Slack. Yeah, there's a question. Oh, we'll still leave some time then. There seems to be some questions bubbling.
So perhaps the unmuting doesn't work?
Should?
Hello, yeah. Actually, my question was this. Can you hear me?
Yeah.
Yes.
So in what way is your work related to inductive logic programming? I've seen a few papers on integrating inductive logic programming to subsymbolic AI, specifically neural networks, to try to infuse some knowledge into them, which you don't get in a statistical learning approach.
Yeah.
I've seen a few papers on that. I'm not able to recall, but of course, one criticism of that seems to be that you have to define all those rules and so on, and rule-based reasoning is a little heavy and time-consuming and so on and so forth. So I just wanted to know your views on that.
Yeah, thanks. That's a great question. So the first part, so this is pretty closely related to inductive logic programming, I would say. And that has been explored by the NeuroSymbolic learning community recently with papers like differentiable ILP and such. And that is, so we pretty much directly adopt that logic programming syntax of ILP. And the only difference is that we make it differentiable as well. And that allows us to use the gradient descent basically to do inductive logic programming, if you like, even though inductive logic programming is more heavily focused on learning the structure of the rules themselves, and we learn mostly the parameters with themselves associated with the rules, which, however, can be turned into the rule learning itself, when combined with sort of regularization or pruning, of those rules that are associated, for instance, with low enough value. So that was the idea of the differentiable ILP, which can be, for instance, emulated in this templating framework as well.
Okay.
And then the other part with the rule-based learning and reasoning being kind of outdated in machine learning, which I completely agree with, is that I would like to emphasize that in this framework, the rules, okay, I won't share the slides again, but hopefully you remember that, yes, some of those rules were kind of heavily involved and complex. For instance, in the planning part, where we were encoding some sort of basic planning policy for the blocks world. But also, they don't need to be like that. They can be completely generic and not encoding some specific domain knowledge, but just like a generic learning pattern, which is what the neural nets are doing to begin with anyway, right? So the GNNs, for instance, GNN rule, it does not say any specific knowledge. It just tells you how should you structure that computational graph, which is exactly the same thing that you do in PyTorch or TensorFlow. It just you use the language of declarative relational logic that might be more appropriate or readable in some cases. And that was trying to argue for that it is more appropriate when talking deep relational learning models. And actually, procedurally encoding a GNN through a series of matrix multiplication, I would dare to say is less readable than this single rule that just says, oh, each node representations is defined based on the representations of its neighbors. That's the rule, right? So hopefully you see there is no specific handcrafted knowledge in that.
So what you're saying is that your rule-based approach is a generalization of that single rule approach of the GNN, which says that a node representation of a node is basically a summation or some kind of a combination of the representation of its neighbors, right? Some mean, average, whatever, maximum, whatever. So yours is a bigger generalization of that. So what you're saying is that you can infuse in some domain knowledge into this through your rules, which is quite different from the standard brute force approach of GNN, that is you just do a summation or some kind of aggregate.
Yeah,
that's what you're meaning, right? Okay.
Yeah,
I'm trying to understand.
You can use those, so you don't need to. You can use completely generic rules that are basically equivalent to existing computational rules that you just define procedurally. But the important thing is that if you want to, you can use that extra domain knowledge and integrate it seamlessly into that existing rules, which is what we did in the planning.
Okay, got it. Thanks.
Because everything in that framework, at least, is just differentiable logic rules.
Right, I understand. Thanks.
Yeah, maybe we'll take the call from Ole Fensk.
So there's another.
Yeah. Yes. Do you hear me?
Sure.
Yeah, perfect. So first of all, thanks for the interesting talk. Maybe another question regarding the structure learning abilities of your approach. So when we perform structure learning within NeuroLogic, is it also possible to convert the learned structural knowledge back into a symbolic and more or better interpretable representation from NeuroLogic, or do we just learn the weights and also the structure within these neural network architecture and are not able to transform it back into a, for example, symbolic representation?
All right, great question. Thanks for that again. So to be fair, we did not focus on the structural learning for the past 8 years also, but we did that originally in this paper, Stacked Structural Learning of the Lifted Relational Neural Nets. That was actually the best paper at the Inductive Logic Programming Conference some 7 years back. And since then, kind of left this subpart and focused on the parameter learning and this interplay between existing neural architectures and not the vanilla ILP, meaning extracting the rules back and then interpreting them symbolically. But conceptually, it can be done similarly to how, some other frameworks like the Delta ILP are doing. But it's not out of the box. It was in the old version of the framework. It's not in the new version because, it was not our focus. That's a fair answer.
Yeah. Okay, thanks.
Thanks. Yeah, we have a question also from the chat. How could neurologic framework be used for knowledge-based completion?
Yeah, so that is, so we also did that in some papers quite some time back. I think that was called learning predictive categories with LRNNs. And yeah, it's pretty similar to the GNNs. So you're just predicting, for instance, the missing link, which would correspond to some atom, a binary atom between some two nodes in the graph that will have the corresponding label of that relation. So it does not differ conceptually from what I was showing in here, for instance, like the learning with relational databases. So in a sense, the knowledge graphs could be seen as a special case of that, even though, so meaning that you can go to higher order relations with the relational databases. Also, I know that there's a lot of subtle nuances with the knowledge graphs, and also the aspect of scaling. So this would not scale to some huge knowledge graph settings where you just want to go with some simpler modeling concepts, such as trans-E or whatever, just learning simple embeddings of the nodes and performing some simple arithmetical operations on those, on top of those, which is essentially what the framework is doing as well. Is just you can compose them into kind of more complex patterns. But yeah, for classic knowledge base completion, you probably don't need all that complexity, unless you want to do some sort of like really involved reasoning on top of that knowledge base, and then yes, this might be more appropriate than simple knowledge base embedding methods.
Yeah, there's another question in the chat, but I saw someone raise their hand as well, so you can go.
Yeah, I did. Sorry. So
yeah.
Thanks for the talk. Really nice. And I haven't seen K-Ben for a while now in a talk, so old stuff is not dying. Cool. But I never worked with GNNs, so to admit it first. But assume that you have a planning domain, say 50 million states, with relations which correspond to actions which you can execute in that 50 million state space. How big would your networks be in total?
All right. So that's a great question. Yeah, actually, I just wanted to say that your paper, Dimensions of NeuroSymbolic Integration, is one of the first one that got me into studying NeuroSymbolic.
Yeah.
Basically, throughout this whole talk, I was just focusing on that single dimension of the problem, which was that expressiveness going from propositional to relational, potentially first order logic. So that's what I was doing. And as for the planning, so basically, if you start the question about classical planning and you say 50 million states, that's already outside of scope of what people do in classical planning. So planning, like in the classical PDDL sense, scales pretty badly. Everybody knows that. Like most of the domains, the actual ones are toy domains and toy problems. So in the existing models, they don't scale, and this definitely won't scale better. To be fair, definitely won't scale better than the GNNs, but even GNNs wouldn't scale well. All right. And the more nuanced answer to this is that the scalability or the size of the resulting network, of course, completely depends on the template which you write down. So if you write a super simple template, such as the single message passing rule for the GNNs, then the unfolded computation graph will be exactly as big as the GNN computation graph, which is linear in the size of the input graph and the number of layers that you want, right? So that's linear complexity. But of course, if you write down some involved complex rules that kind of encode some tricky combinatorial reasoning, then it can explode exponentially in the backend. And yeah, that's an inherent, unfortunate, but kind of necessary property of this relational learning approach, that if you want to have a complex model, then you can. But yeah, if you don't, then you don't. But you have to be careful about what you actually want from it.
Okay, so we have to work on it somehow. So
yes,
because
so
I mean, humans, we can solve these problems. So I mean, if I just look in my kitchen and I check the number of knives and forks and whatever I have there are more than 50 million states possible in my kitchen. So by all the permutations, and we can still solve it as a human.
So you mean like the state space in total, not like the size of the, say, learning data set subsampled from that overall state space? Yeah, sure. Then that's not a problem. So 50 million, that is even probably not enough for a complicated planning problem. So yeah, so that's fine, because of course you're not expecting to visit every possible state in that state space, and that's not what the planning template is doing. It's not unfold, even though you could potentially do that, but that's not what it's doing. It's just working with the current state and the potential goal state, and it kind of combines that in some sort of joint representation, because that's the kind of information you need to know when doing that, classic search routine throughout the state space. You need to know where you are and where you want to get to, and to establish some sort of a distance, like the heuristic, or some sort of ranking of what action to take next. And that's small. That's linear in the size of the state, potentially, with the GNN-like models. And the states in this classic planning task are, few dozens of atoms. So the computational graph will be also a few dozens of nodes. But then, of course, again, also depends on the parameterization that you associate with that.
Okay, we definitely need to test your software. So I want to check what happened if we scaled the problems. But we'll do.
But definitely, the learning is not there yet. We are not able to, and I don't think any of the current learning approaches is able to beat state-of-the-art planning software, such as the Llama or Fast Download or things like that. They are just still better, and probably it won't change in any time soon, I would say. But it's an interesting domain to explore with NeuroSymbolic learning, I would say.
Yeah, and they got faster because they did all this learning in their planning stuff as well. So,
but I would say most of the state-of-the-art are still not doing any proper learning. They are really still heavily optimized C++ code based on known heuristics and
Cool. Thanks.
Yeah, there's another hand raised, and then we can have a few more questions. I know usually we end around 4, but there's still some interest, and there's still a question in the chat. So there's Mohammed with his hand raised, if you would like to.
Yes, hi. Thank you very much for your great presentation, first of all. So my question is, we have did a project on graph neural network on drug discovery. So basically what we did is we do have the compounds or drugs. So we have basically converted those compounds into graph representation, whether the atoms are into nodes and the bonds are into edges, and we have do some sort of graph neural network model to predict bioactivity, which means it will predict the deep neural, which means it's a deep learning model which needs to be predict on the bioactivity, whether it's a good drug or bad drug. And the second part of my project is to generate new drug based on what it learns. We have used a graph invent model, which is invented by the AstraZeneca team. So where I have did the master project on that. My question is, in your talk, does your approach or model will be help for my research in some sort of to enhance my model, or to build up a very good anything you would like to add on this?
Sure. Thanks for the question. So basically, I can't say in advance whether that will be able to help you. The only way to find out is to try it. But we've tried, originally working with the molecules was one of the most common benchmarks for even inductive logic programming or relational learning, now for the GNNs. So that's where the GNNs already excel. So they are the state of the art there. And but there are things that you can do beyond that vanilla GNN models. One of those I was showing, but that is already incorporated in some of the latest GNN models already. And actually one paper that been working on with one of my students for the past 2 or 3 years was doing something a bit more extensive in that sense, and I was taking basically a chemistry knowledge. So he has a bachelor in chemistry, so basically you can use these relational rules to encode all sorts of existing knowledge from chemistry, about functional groups and interesting substructures and things like that, and enhance again the classic GNNs models with those rules, and again differentiate through that and learn on top of that, which can lead potentially to more interpretable and steerable models, which can be kind of beneficial in computational chemistry, hopefully. But yeah, it's kind of like work in endless progress, but definitely potentially interesting. I think this student of mine, I think I've seen him in the participants list. So yeah, it's Amir. And yeah, he has that on GitHub as well. And kind of did his master's thesis on that topic as well. So you can read the details in there. And yeah, reach me out on Slack and I can send you the links.
Yeah, okay. Thank you very much.
Thanks. Yeah, then there was a question in the chat for a little bit here. And it says in the same line of question on ILP, can you touch upon the difference with deprobe log just so the intuition becomes clear?
Sure. Yeah, so deprobe is this recently very popular NeuroSymbolic framework from Levin. And yeah, the difference is pretty simple. So deprobe is a probabilistic model. So we also work with probabilities, while we do not work with probabilities, which is a benefit and it's pros and cons associated with it. So we do not have probabilities in here. So that's clearly not a benefit. We cannot reason about, we cannot reason probabilistically with these models beyond, that simplified neural putting softmax at the end or sigmoid and saying that's probability. So that's not a real probability. Problog can do that. So Problog is this language for probabilistic logic programming. And then recently, the guys from Levin extended that with these neural predicates that can basically, which kind of makes it a NeuroSymbolic approach. And so the con is that you do not have probabilities. The plus of that is that probability calculation, especially the normalization to have actual probability distribution, is computationally very expensive. So that scales even worse than this. And so Problog doesn't scale very well to large tasks, but definitely is a very solid NeuroSymbolic learning. And also like the integration in the Problog, although they probably like to present that it's the full NeuroSymbolic learning package, because they have the probabilities, they have neural nets, and they have logic. And it's true, but kind of the integration aspect from my perspective is a little bit lacking, because like the interface between the neural port and the logic programming port in there is pretty narrow. Basically, it's just about sending the values there and back, like scalar values, like the probabilities. Whereas in here, for instance, in this framework I was showing, the integration goes much deeper. You like literally using, so they are kind of agnostic of what neural architecture you're really using for those neural predicates. It can be a standard CNN. It's an outside call to some existing deep learning package. Whereas in here, with the rules, it's deeply integrated, as you can like directly use the rules to encode the neural nets, and everything is differentiable logical rules. So there is no outside call. It's also like, for instance, written completely from scratch by myself. So we don't have probabilities, the biggest difference, which makes it scale a little bit better. But of course, the disadvantage is that you cannot reason probabilistically with this.
Thank you very much. Yes.
And I think there's a last question in the chat. Maybe if this one is our last, unless there's a last chance, maybe just last chance. But this is a question. It says, one interesting extension of this work could be to use the domain ontology to derive the rules. What would your approach be compatible with that?
Yeah, I'm not sure I completely understand the question, but definitely like using rules from some existing domain ontology for that templating is a very sensible thing to do. So if you start with some domain that somebody already mapped, meaning that they created the ontology for that, including the data and also the rules, then, well, most of that. So basically language here is data log, where in the ontologies, you can possibly probably go a bit beyond that with this other subsets of first order logic. I'm not sure now exactly what those Schoen, Schroik subsets now are, but definitely a lot of rules, like inheritances and standard like classifications of objects and that people normally use when modeling ontologies can be used as rules in the template and then differentiated through in that aforementioned sense. So yeah, that would be a good starting point if you're learning with some domain that's already mapped to an ontology to use that existing background knowledge.
Thank you. Well, maybe I will direct future questions and discussions to continue in the Slack, NeuroSymbolic Slack channel. So yeah, I'd like to thank you, Gustav, for your great presentation and for taking these questions. And we will introduce the next webinar also in the Slack chat. So keep an eye out there, see when that will be. And yeah, I wish everyone a great day. Thanks for joining.
Thank you.